installed, etc., etc. Okay, just 1 second. I just wanted to highlight that I still have an old version. I have 3.6.3, which is 2020, and probably I may update it, but it's not really a problem. Okay, now you have in your R window, you have also menus. Let's forget them for now, okay? And just ignore the menus. R, it's a software that has been conceived to be used without using the menus. And they are there in Windows, and not in my environment. They are there just because it's an aid to provide some shortcuts. And the menus in Windows in general, the menus are created for allowing you to make with the mouse operations that otherwise you should pass through the keyboard. And therefore using the mouse may be quicker. So Windows also with this software that was conceived for a generalistic environment, a general environment, Windows makes an attempt to provide some shortcuts, but let's forget about them for now because they are not really useful, okay? Okay, so far so good. Let's clear the screen with Control L. Control plus L at the same time. Now, as I said, the console waits for commands, and it's an interaction between the computer and the user, which is not very user friendly, because you need to know what commands and what language R understands. So let's suppose that I want to compute 2 plus 2. I need to know how to speak to R, how structure, how I should tell R to make the computation 2 plus 2. This is a naive question because actually the command that I should give to R for computing 2 plus 2 is simply 2 plus 2. And then if I press return, I get 4. And same thing, 2 times 3. And same thing if I want to use the parentheses, 2 times 4 plus 2. I am expecting 12. Here it is. Okay. So basically, for this simple computations, it's not a problem. The language is naive. It's I can get it also by using intuition. Okay. But on the other hand, for more complicated operations, I need to know the language. For instance, let me suppose that I want to compute the square root of 4. Of course, I can do this. I can type 4 elevated to 0.5. But in case I wanted to compute the square root, R gives to me another opportunity. So I don't need to necessarily elevate the number to 0.5. And how can I then explore these opportunities? How can I explore the R language? Okay. Or let's suppose that I want to compute the logarithm with base 10 of 10. How should I write the function? How should I write the command? Okay, of course, I can read the introductory guide to R. This is possible in order to learn the command. Another option is that, given that it's an open source software, let's go to the web and let's go again on Google.com, and let's make a search with keys R project and square root. And then let's click on the first link, calculate square root of a number in R language. Let's wait for it. And you see that it says that you may write it in this way. Just 1 second, consent. Okay. You see sqrtx between the value of x should be given between parentheses. Let's test it. Sqrt for 2. Good, perfect. Logarithm. Let's go back to the Google page. Our project. Logarithm base 10. Let's click on it. You see it's log. Let's look here. Log computes logarithms by default natural logarithms. Log 10 computes common here base 10 logarithms. Okay, so let's try log 10 of 10. 1. Good. Or log 2 of 2. 1. Very good. Let me clear the screen now. Just let's also make this attempt. Log 10 base equal 10. 1. Good. Now let's make some considerations. First of all, logarithm is a function, what is called in R a function. It's a particular type of command. A function is making a computation depending on some arguments. The first argument of this function logarithm is x, is the number I should compute the logarithm of. The first argument is the number I should compute the logarithm of. There might be additional argument, and if there are, they must be separated by commas. So look on the screen. Log, the first argument is the number 10, and then there is a comma, and there is a second argument. The second argument is base equal 10, which means that I have the opportunity to specify the base, and by giving to me the possibility to give to the base any number. Okay, so this is an example of how an argument is to be a function is to be used. I have to give the arguments between round parentheses. Now let me compute it again. First of all, in order to get back the previous instruction, I typed arrow up. With arrow up, I can get the previous instruction. Let me write here x equal 10. I get the same result because arguments have names, and some of them have default values, which means that I can, if I want to be more rigorous, give the name of the argument like I did in the second line, log x equal 10. Or if I omit the name, I must give the arguments in the same order they are given to the function when the function is written. So in order to use a function, I need to know a few things. First, the name of the function. For logarithm is log, for square root is sqrt. Okay. Second, which arguments I am supposed to give to the function. by keeping into account that some have default values, and therefore I can also not provide them. But those arguments which don't have default values, I have to provide them. Third thing which I need to know is the order of the arguments, because in this case I can avoid to write the name of the argument like I did in the first line. I didn't write x equal to 10. I just wrote 10 because I knew that the first argument that the function is expecting is the number. Next question. How can I know all of this information? How can I know the list of the argument, the order, and so forth? There is, of course, the opportunity to better read on the web the instructions. So let me go back to the web page, and you see here the description, usage. Look at this line that I am selecting. There is written log, and then the arguments that the function is expecting. So the arguments are x, for which I don't have a default, and base, for which I have a default, which is given by what is written after the equal sign. Okay, good. So in this way, I could understand what are the arguments, what is their order. Perfect. Now, let me make another attempt in R. So after I looked at the web page, I understood that I could give the argument without specifying the name. And you see that I get the same result because the first argument is the number, is x, the second argument is the base. Perfect. Another interesting thing, if I type $log, I get an help page which says the same thing that you can find over the web, but it is quicker. It is quicker to get help from R. The only problem is that you need to know the name of the function. So here I could invoke R help because I knew that the logarithm is called log. The function to compute the logarithm is called log. If I ask the help for logarithm, and you see that there is no way, just 1 second, because I have amnesia. No, it is also misspelled. I'm sorry. Logarithm. Logarithm. No, it was not misspelled, sorry. So you see that there is no documentation. So in order to get the help from R, you need to know the name of the function. In this case, we didn't know it, so I prefer to go on the web. Good. So we learned some commands, or better, we learned a category of commands into R, which are the functions. Perfect. Now, let's move a step forward. Assignment of variables and vectors. Okay, let's try to write a equal 3. It is memorized as a variable. Now, if I type a times 2, I get 6. Good. It is a way to put into memory numbers, or also characters, as we will see. How can I know what are the variables that I memorized? With a list command, it's a function actually, ls, and then I need to put 2 round parentheses, and you see that it gives a list of the variables. You can assign to the variable any name. I could write my variable equal 10, equal 9, and then type a times my variable then if I take the list, now I have two variables. Good. Now, step forward, vectors. Let me clear the screen. In order to assign a vector, you need to use a function. So my vector is equal to, this function is simply given by the letter C. The arguments are the elements of the vector. So this is an example, and if I type now my vector, I get the three values that I put into the vector. I could have written something like my vector. Look, if I define another vector with the same name, I am overwriting the vector that I previously defined. So I could write my vector is equal to C, A, my variable, good. And now if I write my vector, I get 3 and 9 because my variable is equal to 9 and A is equal to 3. Okay, now I can make operations with the vectors. My vector times 2. Each element of the vector is multiplied by 2. Whatever. So I can use them in normal operations. Just try to get familiar on how vectors are dealt with in R when computing operations. For instance, if I write my vector plus 2, what I obtain is adding 2 to each element of the vector. Okay, now let me clear the screen. I can also define arrays, like my array is equal to array, and then let me put here as the first argument 0. It means that the array is filled with zeros. So my array is equal to array, and then I have to give the dimension. The second argument is the dimension. I can give the vector 2, 2 to define the dimension. And then if I write my array, I get this. Arrays and vectors can be used to make multiplications of arrays with arrays, vectors with arrays, etc. If you make any operation involving arrays and vectors, again, make sure you understand how R performs these computations. Okay. I think now it's time to say a couple of things, important things. Into R, there is no option to undo any operation. So for instance, if I remove my array, look, my array now is memorized. You see the list of the variables, vectors. There is my variable, my vector, my array, and A. If I remove my array with the function rrm, and then I make another list, my array disappeared without asking me to confirm, with no way to get it back. There is to say that R, as we said, preserves the previous command, preserves the history. by using arrow up, I can redo what I have done before. So if I want back my array, I use arrow up to the definition of my array, and I can create it again. So it's true that we cannot undo, but it's also true that we can repeat very easily what we have done so far. And therefore, it's just a matter of getting into a different context, a different perspective. You cannot undo, but you can redo everything. So actually, I don't suffer the lack of the undo command. Another important information, how to save. Okay, so far I worked and I saved some variables, and I also have an history into R that allows me to redo what I have done. But if I get a crash of the PC, everything disappears. It's not automatically stored over the hard disk. To save, you have a couple of different options. The first one is to use the function save image. Just 1 second, because save image. Save that image. Okay, sorry for that. Save image. And with save image, you save your variables vector arrays. When you start R back, they are still there. Okay. And with save history, you save the history. So if now you go out from R by writing the function Q, followed by around parentheses. First of all, it asks you, do you want to save everything? This is another way of saving. You go out. In this case, I already saved, so I can write no. So I didn't save anything. Let me restart R, clear the screen. And if I use the arrow up, you see that I still have my previous commands, and I still have memorized my variables, which is okay. It is perfect. Okay, so sorry, we learned how to save, which is an important information, of course. And now I think we can start looking at our exercise. I mean, we learned a very little bit of R, a very tiny portion of it. There is a lot to learn, and we are far from being independent at this stage. On the other hand, I prefer to take a practical, empirical approach by adopting the philosophy of learning by doing. I prefer to learn how to use R by making a practical exercise related to Harbour engineering. So learning by doing, I think it's more stimulating, and it's more targeted. Of course, learning by doing implies that you don't learn anything. In any case, you wouldn't learn anything, but learning by doing gives you a very sectorial type of information. So don't forget this. Don't forget that you may feel like you are a very good R user after having completed one of my exercises. On the other hand, don't forget that this is a very limited perspective, and actually you will learn a very limited number of functions, and therefore if you want to integrate this preparation, you will have to dedicate some effort to either making many exercises or studying the quick guide a little bit, or getting information over the web, whatever. Just be aware of the kind of skills that you are gaining. So let's go to the web page now, and let's then refer to the exercise. And let's look what is the exercise about. Here we see computation of wind actions on a moored ship and computation of mooring forces. Very good. Let's click here. And we get to another web page, which actually is structured as a lecture. Okay. But in reality, this is an exercise. Okay. Let me just log out from my website, because in this way it's more manageable. Okay. Here we are. So let's read it. A ship with a displacement of 3,350 tons, a waterline length of 117 meters, a draft of 5 meters, a beam of 12 meters, pivot point located at 55 meters from stern, and the side projected wind area of 1950 square meters, is moored to a berth with the 6 mooring lines displaced as in figure 1. The mooring lines are the red one. The yellow ones are mooring lines that are frequently used for especially for big ships. We are not including them here because of simplicity. We want to simplify the exercise, but just keep in mind, as it's written here, red lines are the mooring line that I am considering. The yellow lines are additional ones that are shown for the sake of illustrating further possible lines. Okay. Now, let's look at the wind forcing. The ship is subjected to an extreme wind velocity of 50 knots, about 92.6 kilometers per hour, with wind direction perpendicular to the ship center line. So it is the most disadvantaged situation. The ship is moored with mooring lines composed by 3 ropes of cross-sectional area of 30 square centimeters each. The elastic modulus of each rope is 125 kilonewton per square centimeter, and the breaking tension is 25 kilonewton per square centimeters. Now, at this stage, we have to compute the wind force and the yaw moment. Compute the mooring forces and safety factor for mooring lines by assume that the ship is moored with the 6 mooring lines that are depicted in red in figure 1. By assuming that the origin of the axis is placed over the pivot point, and assigning the following values to bollards and chocks coordinates, where X is along the ship center line and the Y is along the transversal direction. So we learned here some new terms, okay, like what are bollards, what are chocks. Bollard, I think we know what is. It is the anchor point of the mooring lines over the berth. And then there are the bitts. The bitts are the anchor point of the mooring lines over the ship, and the chocks. The chocks, we mentioned them in the last lecture, are the holes through which the mooring line passes in the both side in order to limit the inclination of the mooring line themselves. let's look in Google chalk ship, and you see the images. You see the chalk is a kind of window in the boat side to get the mooring line through the body of the ship without passing over. Good. So we have to compute then the mooring forces according to these coordinates of the chocks and the bollards. Actually, it is a frequent practice when computing mooring forces to refer only to the length of the mooring lines between the chock and the bollard. Now, to make the computation, we can assume that the mooring lines are horizontal. We can assume that the coefficient CW is 1.3. And we can assume that the mooring lines are 15% longer from bitts to bollards than the distance between the bollard and chocks. Bene. Well, okay. Let me refer to an example of our code that is given here. So here, if you click here, we should find an example of our code, and let's wait for the download and let's open it. It is opened, just 1 second. No, let me put the open file on the screen. 1 second. Okay. I think I need to open with okay. Kate. Let me put it on the screen. Here we are. Okay. This is an example of a sequence of R commands. You can recognize in some of these lines functions which I used during my introduction to R. So the first thing that we have to do is to compute the wind force. Now, the instruction is this one. In order to compute the wind force, which I think it is the last task that we can perform today, we have to apply this formula here. Let's get back to the web pages. You see, this is the equation for computing the wind forces, which you can find in the lecture, which you may remember, dedicated to forcing estimation. If you go down, you know this lecture because we dealt with it last week, and we get the formula for the computation of wind forces, which is the same that you can see here. Okay, good. Now we need to know to apply this formula, the coefficient CW, which is 1.3. We need to know AW, which is 950 square meters. We need to know phi, which is 90 degrees, and we need to know the density of the air, which is 0.01225 kilonewton cubic meter. And then we need to get the wind velocity, which is given by the exercise, and the value for gravity. But once these values are plug it into the formula. Computation is straightforward. Let's make it in R. And let's first make it directly here. Okay, so let's see if we can, yes, we can have a look at the formula, and we can try to type into R PW is equal to, remember that R makes a difference between lowercase and uppercase. So PW is equal to CW, it is 1.3, times, let's open a parenthesis, AW is 950, times sin 90 degrees is into R, the angles must be given in radians. So 90 degrees is pi divided by 2. I don't remember if pi is, let's try pi. I'm not sure whether it's whether pi is given by the name pi, but we can check. We can try. Sin I would, it's sin square. So I would prefer to put a parenthesis here and square the value of the sin. Okay. Plus BW. BW is let's see. BW is 0 because now we can forget BW. Why? We can forget it because cos square of 90 degrees is 0. So BW can be forgotten. So I can close the parentheses. And then I need to multiply it by the air density, which is 0.0225. And then I need to compute it, to multiply it for the square of the wind velocity. And it's 25.72 squared divided by 2 divided by G, 9.81. Let's see if it works. It looks like it worked. Let's see the result, what is. It's 510 kilonewton, which seems correct. Correct because if I look at the web page, you see that it's very similar, the value that I find here. There is a small difference, which is probably given by, probably I forgot a digit, I'm not sure. Or, okay, let's see, pi then worked. Yes, it works. Pi is the correct name into R for pi. So we already computed the wind force. And this wind force is applied to the center of gravity of the wind edge area. Now, to finish up, let me clear the screen and let's look at my proposed R file, which was here. And this R file makes the computation of the wind force. Where is the computation? Just 1 second. Here. You see that it makes the computation in the same way, with the only difference that it uses variable for CW, side area, alpha, and the velocity of the wind. These variables were defined somewhere. They are defined here. They are defined here. And in a way, they are defined in a way that I'm not anticipating now, because they are given the default values by writing a new function, which is something that we will explore next time. Okay. I just wanted to say that I could come to the same conclusion if I into R, instead of computing this function, I am recalling it, I could have defined all the variables like CW equal 1.3, and then I could rewrite the same equation by writing here CW. Okay. So this is what is proposed in my proposed R file. It is proposed that you first define all the variables and then you make the computation. It is preferable when you have to make the same computation several times for different values of the variables. And therefore, it is more convenient that you write the computation just once and you rerun it by changing the value of the variables if needed. Okay, I think I can stop here. And also, you know, it's 4 hours, it's extremely long, and with the limited audience, it's also the velocity, the pace of the teaching is a bit faster. So I think it's time to close this day. Do you have any question if you're still there?
Of course, I'm still there, Prof. There is no question. Yes. No, thank you so much. Thank you so much. And grazie.
Prego, now I am sharing the screen and I am stopping. I will make the video available soon. Thank you once again. Bye
Thank
bye.
you so much. Ciao. Bye.
Ciao.